And I would like to start, I should frame the picture like Matthias here. I'm going to bring you not to Switzerland, but to a mega city. And as you can see here, these mega cities concentrate high density and huge ambition for vertical growth. But on the other hand, you can also see a high vulnerability of this whole infrastructure. And so the question is, how could we harness all these opportunities we have? We've heard from Georges, there's a lot of opportunities to drive such systems, which is highly vulnerable, to some desired future. And I'll try today to explore with you if we can bridge the analytical capacities of science with the creative possibilities of design to chart together resilient pathways for these futures. As I said, on the one hand, we have huge vulnerability of these cities. They concentrate economic activity, infrastructure, and a lot of people. And you can see on the left side a recent study which nicely shows in one message is that urban systems are accelerating the risk, the problem. You see the blue curve, which presents the city under global change, global climate change, with an increase in temperature. But if we consider the urban warming itself, so the city, how the city produces heat, you can see that many more people are under risk in these situations. On the other hand, you also see the risk created by floods, for example, an amazing increase, a quadrupling of the risk in the last 30 years. And you can see especially in Asia, but if you look very clearly on the bottom line, you see that there's an exponential growth also in Africa, where a large part of the population is going to grow. On the other hand, I said cities provide huge opportunities. A lot of people live there. And what you can see here is all the services which are provided just by open space in these cities. They range from coastal protection, carbon storage, recreation, nutrient cycling, etc. And we've quantified in a large project, for example, for Singapore, how much this would be worth. It's a lot of money which is created also for the people living in these areas. And you can see that around 1.9 million would be provided by carbon storage, or that we could reduce air temperature with these green areas by around 4 degrees. And people would even be willing to pay for air purification. We see also the importance of mangroves for protecting coastlines, soil erosion, or the vegetation, which can temporarily retain rainfall, or the activities you can get, and even the health effects of these green areas. So when we talk about trying to harness these opportunities to drive the system towards a resilient system, I would like first to just open a little bracket, because I think a lot of people here are very technical, and I think we have a different understanding of what resilience means. A lot of people think about resilience as something which is effective, which is something which is going to buffer against the changes, but in an effective manner. However, sustainability and resilience are not necessarily the same. Let's think, for example, about a system which is very effective. It's not redundant against change. You remove certain parts of the system which could absorb the changes in your system. So we usually very much on the lower corner here with business as usual, where we're not very sustainable. So we probably need to improve the waste sector, energy consumption, etc., which we can optimize, which would increase sustainability. On the other hand, if you only would do that, we're not very resilient, because we don't have local redundancies. We don't have a bottom-up management, so a stewardship for these systems. So if you really talk about resilience, or if I would define resilience, I would try to reach this upper corner here, where we try to design something which is diverse, redundant, cross-scale, and has a collaborative governance. And not only in one point in time, but over time. So we need to have such a system which is diverse, redundant, with a support, a bottom-up support, but which functions over time. Which means that if we have a pathway, here you see different pathways, that this system can absorb the change over time. It's like this corridor you can see here. It's like a tunnel. And this tunnel is allowing to stay on a certain pathway over time under different climate and socioeconomic changes. So it's resilient over time. And what it also shows is that this resilience, maybe you're resilient, but you're locked into one of the pathways. You can see that you might be resilient, but you might provide very low services, ecosystem services. So sometimes we need to think resilience as a chance, if it's low, to change the pathway with an abrupt transformation. So sometimes you need to reduce the resilience to be able to come to a new pathway. And that's where a lot of nature-based solutions come in. They try to unlock a certain pathway and to get you onto another pathway which should be resilient to the certain changes. So diverse and provide services, ecosystem services, for example. In the science I'm coming from, we would call these seeds of a good Anthropocene. Seeds, because they make something grow, they're innovative, but they're context specific. They're anchored in a context and they are diverse. And I'll come back to this little picture you can recognize here from the Petit Prince de Saint-Exupéry, who plants his little rose. And we'll come back because also he puts a seed for certain things we need to tame to become responsible. So these seeds, we're going to look at them. The problem with these seeds is that you will see that many of them are not really transformative. We see here an analysis, quite recent analysis, of 550 nature-based solutions. And you can see what they could involve. They could involve vegetation features. You would just add trees, for example, or some parks, or some green roofs, or some green alleys, or you can go into the blue infrastructure, where you can have some stormwater basins or constructed wetlands. Looking at the challenges, we were talking about urban heat island and flood. You can see that they're all along this bottom line, which is very much constructed. So we're designing the system to provide us certain solutions for regulating our system. We call them regulating ecosystem services. What we also see here is that to really get an answer to these outcomes, biodiversity, health, regulating, one will not suffice. We will need a combination. We'll need many of them, a diversity of them, to be able to address these outcomes. The problem with these nature-based solutions is that very few are really working. Very few are changing the pathways. They are usually very incremental. I have to say, when I've walked here through the campus, are they really working? Are they really providing us a new pathway where it really gets cooler in here, where we really have water retention? Or are these few trees an exercise where we try to have some nature-based solution, but the functionality is not really provided? And what we've seen is if we analyze these studies, only about a fifth of these are really transformative. And when we talk about transformative, I said they need to be past shifting. They need to restructure the social and ecological system, so how people interact with nature. They need to function at multiple scales. So does this function at multiple scale? I'm wondering. They need to be innovative. They need to be system-wide and persistent. And when you look at these green areas here, you will see that it's not easy to implement. It needs 3 spheres, and these three spheres come from O'Brien. She talked about transformative and how you can transform system for climate change. And you can see that you need, at the basis, to change something in a practical manner. But this needs to be embedded in an institutional setting. So you need rules to transform this. You cannot just transform it. You need certain rules, institution who supports that. And to have institution, you all know, we need a political system which is going to frame these institutions and select them so that they can perform. This is why I would like to suggest and explore, as I said with you, a little bit a different way to think about that. Why don't we enter the system with design? And I think there will be another talk about design, which I think is going to be quite interesting to see how you see this importance of design. But a design which is informed by science. So not just designing, but having ideas, innovative ideas, unlocking the pathways, and informing these designs by science. So applying your fantastic models to try to understand if these designs function. And to do this iteratively in a process which could support the implementation later on. So to do this so that you get people to have a responsibility for this design, which at the end should function. So this design science loop is not totally new. It's not that we invented that, really. But if you go 100 years ago, more than 100 years ago, and look in philosophy, that was a little bit already the thoughts, for example, from John Dewey, who at the beginning of the century was thinking that science is just a timeout. It's a timeout, a reflection of the real implementation of reality or solution of reality. So that you reflect on what you're doing through a scientific process. And this idea of that science is a knowledge of affair in terms of a timeout has been taken out about 100 years later by Donald Schoen. And what he said is that it's even further. To really do science for a real-world problem, you need to put it into action. You need to test it into action. Because otherwise, you will have something which does not really function and is not really taken up by the local people. We use now another way to define it. We talk about informed design, which we would define as a new idea, which results from a collaborative process, which takes into account aesthetics, functional, contextual, cultural, and societal consideration of the system, and is supported by scientific reflection. So not science is the real result, but the reflection will help us to create something which works and is a solution. And you can see a good example of such a science design loop or informed design, which was quite old in 1970s in California. The park, the Levins Park, which was designed by Halprin, which was designed for drought, and you know how California is exposed to drought, without having these really situation at that time. So there was already this thought, we need to have certain systems which need to function under different consideration and boundary conditions. So we thought, okay, well, if we really want to have this science design system, we need to understand how it needs to be integrated in a process. We said it's not just science design, but it's a process itself so that people then are responsible for this science design loop. So we analyzed different case studies. Case study of nature-based solution across the world. And you can see, I might help here. You can see here the science design loop, which is embedded in a large process. You can see in gray, this is the part where people are involved. And the yellow here is the governance. The blue is the science, and the red, the design. And what we see here is that in Singapore, the ABC water project, which was initiated really to address flood and droughts, you can see that the design science loop was really very, very shortly integrated in a participatory process. It was just used to analyze these different designs in terms of the users. If we go to the Sponge City a project in China, there are many and different ones, we can see that it's a very strong political process, an idea, a goal they want to reach. And what we can also see is that it's very much driven by design, and the functioning is very poorly usually made in these projects. You know that they need a lot of money to really function. If we go to Switzerland, which is of course not a city, but what we see here is that we are in a much stronger public consultation system. It was the Rhone correction, the bringing the Rhone to larger space. And what we can see here is that the process has very much been integrated in the design science in a public consultation process, but at the end, they were implementing it stage by stage without taking people into account, which made a lot of problems. Finally, here you see at the bottom a project of rehabilitation of the Ciliwung River in Jakarta, which was very well done at the beginning, but was not being implemented because we were missing participation here at the very beginning with the definition of the context. So when I talk about a good design science loop, if we want to bridge it, learnings from these case studies show us what we need to do. We need to have a very early understanding of the context and understanding what are the problems. We need that to iterate this design and the assessment of the design. And then this informed design need to be shared with the people to understand what are the problems in the implementation. And I'm going to go through these different steps with you in a real case in Madagascar. I'll come back. But before I do that, I will need to introduce a methodology which allows us to do all these steps together. So with science, design, and people. And this is what you can see here. It's a point cloud. It's a LiDAR point cloud. In this LiDAR point cloud in Switzerland, we have a fantastic 3D LiDAR data set. And what it allows is to allow first to get the context in a very easy manner through terrestrial laser scanner or also airborne laser scanner, etc. And it allows simultaneously to model certain impacts we want to understand from the design. So this, and you will see, this point cloud can be modified by the designer and directly calculated what is the function of this design in terms of the services provided by these changes. So let me move to Madagascar, to Antananarivo. It's the capital. It's at the 1,300 meter. And you can very nicely see that this city is built in a floodplain, and that the little hubs you can see here are on little hills, which are not flooded. And you can see that this whole floodplain is a huge production of food for the city. So still 40% of the food production consumed in the city are produced by this floodplain. And of course, your brain probably directly links it. This floodplain is more just a food production, but it's a retention basin. Very clearly, it retains the water in these times where there's too much flood, too much rain, but also when it's dry, it provides certain water capacities. And you can see that this system is hugely dynamic. What you can see here in blue is everything which is floodplain. In orange, you can see what is a hill or something which has been built. And you can see that there is a very strong change over the years and over the year between flooding and drought. And what you can also see if you look very carefully is that these large area, these brown area, are the backfilling of this black floodplain. If you compare the rate of the backfilling, so you put earth into the area to create city, and probably people have worked in Singapore, you know the range of such backfilling. You can see here that this city is growing extremely fast, and if you compare, for example, rate of deforestation with rates of backfilling in these areas, we have very similar, very fast changes in these systems. And this, of course, has impact on the services we discussed before. And you can see here one of the effects. That was Hurricane Anna, which had huge impact on the city. It's a regular situation where we have these large floods. And you can see here that this whole floodplain is not really functioning anymore. Everywhere where it's orange, the dikes and the water infrastructure is not functioning. And of course, this is not only a problem for the infrastructure, but it's a big problem for people, especially in formal settlements, which had their houses on these dikes, which were, of course, destroyed and had to be evacuated. So the first thing, as I said, is to identify what are the challenges with these people, which we did in a very intensive manner with all types of decision makers. We heard from George, it's incredible how much interest and claims we have on these areas. And we needed to understand what is the system, what is the challenge. The second thing, to analyze the context, a lot of people do the same thing, is to look at land use change, and to understand what are the land use transitions. And you can do this with remote sensing, but you all know that remote sensing is not really going to be coarse or specific enough to really show us what are the land use in these different areas and how they change over the years. And that's why we had to do a lot of interviews asking people. So we did more than 500 interviews asking, what are you doing? Why are you doing this? And what have you done in the past? And you can see here these main land use changes which are happening, leading to this urbanized zone. So first we have these beautiful paddy sectors, which are then not functioning anymore because we have a change in the climate. We have people cannot produce rice twice anymore. So what they do is only producing rice once a year is not enough for food. So what they do is they start to build some holes to create swamps. And the holes are not just holes to create fish ponds, but they take bricks, and brick material is a lot of money. So they sell the bricks here. You can see the brick production during the drought time during the year. And you can see here the result of the ponds. Based on that, they still need to produce some food, and they're going to do raised gardens, which is an extremely good adaptation to drought and flood. You probably do raised garden in maybe yourself in your little garden, is to do these little gardens which are a little bit higher up. And what they're really good at is that they can produce vegetables at a very local and very small area, which provide much more money than if you have large rice production. And on the other hand, if it's flooded, it's not going to destroy your culture. So a very good adaptation. But of course, if you compare it to how much you could get if you sell your land, it's of course, the next step is to change it to urbanized areas. And you can see this change here in the multifunctionality of our floodplain, which decreases over time. So you can see here the ecosystem services, and you can very nicely see that the water availability is decreasing strongly. Of course, also the aesthetics is going to change, the food production, and the rice cultivation. And you can see that this adaptation system here with the rice gardens was quite a good adaptation, providing multifunctional use of this landscape, but we see that we're not far enough to be able to keep all these multifunction for these changes which are happening. You can see here this backfilling, the speed of the backfilling, you can see here, and the changes which are related to that. But what we can also see, it's about 0.75 square kilometers per year. And this area you've seen in the first picture is quite big. So we can still intervene. These systems have a big opportunity to change this pathway. So we said, okay, well, let's work on changing that pathway. Let's try to get such seeds at a larger scale. And what you can see here are the changes, first, the analysis of the system, and then with the same point cloud, we started to design them. We started to create new dikes, planting tree, new topology, which would support another way of keeping the water while supporting agriculture productivity. You see here these final designs. We did this during 5 years in terms of iteration with the people. And this is one of the design which is going to be implemented. You can see here one place where we would keep the area as a pond to also have certain fish production. You can see the urbanized areas around this large floodplain and the rehabilitation of the dikes and the water system for this agriculture production here, where you have to imagine that one farmer has less than 1 hectare of agriculture production, so they need together to function to create that. And here you see these modeling of this water system. So we use this point cloud to iteratively simulate what would be the resilience of that system under a 50 years flooding event, where you can see here a zoom in into one of these areas and the effectiveness of this design for these changes which is coming up. So you can see here the final design. You can see here the 3 areas of intervention. And you can see in gray, so these are the areas where we intervened. And you can see here how the water modeled can then provide the real services needed for the system. Of course, you might come and say, well, but how do you implement this at the end? We have a nice design. We've taken people on board. We've done that many times. How can we know what we need to do? And I've seen that there's some gaming, serious gaming sessions this morning, for example. We also developed a serious game. A serious game is a platform for negotiation, where we invited decision makers, but we also did the serious game with local people, and we tried to understand what do we need to have this system transform. So what do we need? Do we need other governance system? Do we need other rules? Do we need other collaboration to make this system change? And you can see here the elements, and you might want to see here that there's a lot of green and blue, so this blue-green infrastructure. And we played this several rounds with a lot of different people. You can see here, on the one hand, with a lot of decision makers, but on the other hand, also with a lot of local people in the different neighborhoods. And the results are very clear, is that first, there is very little collaboration, intersectoral collaboration. And without this intersectoral collaboration, so the agriculture, the spatial planning ministry, there will not be any transformation. And the big problem is that the visions of all these stakeholders are extremely different. These people have other expectations of the transformation of this system. And what is also problematic is that the vision of the local people are very different than the ones from the decision maker. So we are at the moment in the process of developing new rules with the ministry. We have money from NGOs to make the change in the areas. And of course, this needs also a lot of work to get these people working together and have acceptance for these transformations, which will require people to work together to make this situation happen. So to finish here with an example, we think that we're going to be successful. We had done the same exercise in Jakarta at the Ciliwung River, where we went really far, but it was never implemented. We are hoping that this time we get to the step of implementation by learning of what we had done previously wrong. And we see that such iterative design science loop can really help to think about systemic change, so changes which are radical. Here the radical changes are new topography, a rehabilitation of the dike, and also a new use of this landscape, supported by informed design, and which increases also the stewardship from this local people. And that's why my little Petit Prince comes in, and he said, you become responsible for what you tamed. And I think this responsibility needs to be created if you want to have a transformation. If you want to have a disruptive transformation, you need to have this support so that you can really change certain things and upscale it. And this needs a shared vision, and we've seen that that's very difficult to get. There's a missing discussion, an opportunity to discuss. You need to negotiate these trade-offs, who wins and who loses. You need to involve the diverse actors. And at the end, you need to have the knowledge. You need to transfer knowledge and develop knowledge together to be able to have this transformation. So this co-design is a little bit the mediator between the now and then and can help us chart dynamic, resilient pathways. Thanks.